All right, in this video, we're going to be discussing vectors, both a geometric and an algebraic approach. So this is combining lessons 2.5 and 7.5. Now, many of the quantities in the world around us have both magnitude and direction, while others only have magnitude. And quantities that have magnitude and direction are called vector quantities, while quantities with magnitude only are called scalars. And just to give you kind of an idea about the difference, scalars versus vector quantities. So if you were to say, I have 10 jelly beans, that's a scalar quantity. It doesn't matter what direction. There is no direction for jelly beans. But if you're saying I'm traveling 10 miles per hour north, that's a vector quantity, because here you have a magnitude and then that's your direction. All right. If you give your height, that's a scalar quantity. Your height is just some number. You don't put a direction on it. You don't say I'm 6 feet up versus 5 feet down, so on and so forth. Okay. Now, one way to represent vectors geometrically, if you're going to be drawing them, is with arrows, and the arrow indicates the direction. So where the arrow is pointing, it represents the direction of the vector quantity, and then the length of the arrow, how long that vector is, corresponds to the magnitude. So the larger the magnitude, the longer your vector would be. And so a vector can be represented geometrically by a directed line segment with an arrow head, and the arrow specifies the direction of the vector, the length describes the magnitude. Now the tail is the initial point, and then the tip of the arrow is the terminal point of the vector. That way you know where you start and where you stop. And vectors are denoted by lowercase boldface type. That's when you see it printed in a book. Now, when we write it out by hand, we can't write bold. So when you want to indicate that you have a vector, you put this arrow on top. But when you see it in a textbook, it's going to be boldface like here. You see that? Now, with vectors, real numbers are scalars, and scalars are denoted by lowercase italic type. So if the initial point of a vector v is p, and the terminal point is q, we write vector v as pq with that arrow there. So basically that would mean vector v starts at p, ends at q. Here's p, here's q, and then I would put the tip of the arrow there. That's vector v. Okay? Now, a position vector is a vector whose initial point or starting point is at the origin, is at 0, 0. Okay? And a lot of the time, it's very useful to rewrite a vector as a position vector, because then you can understand its direction and magnitude a lot more easily than if it starts somewhere else, okay? And in order to write, in the first example here, write a vector as a position vector given the initial point and the terminal point, what you need to do is basically take V and do terminal minus initial, okay? And the way you indicate that you have a vector quantity instead of an ordered pair is by using these brackets here. So they're telling me the initial point is P and the terminal point is Q. So you're going to take the x coordinate of Q, terminal, -3, minus initial, which is going to be the x coordinate of P. And then my new y component is going to be -4 minus -2. Okay, so this would be -3 plus 5, which is 2, and then -4 plus 2, which is -2. So here's our vector. This is the x component, and then this is the y component. Okay, and I want you to understand that these are the same. So vector PQ versus what we just found here. So let's just do a quick little sketch. So P was at -5, -2, 3, 4, 5, -2. So here's P. And Q was at -3, -4. There's Q. Okay, and it went from P to Q. So I put the arrow in that direction. Well, I rewrote it as a position vector, that vector V, and I have that the components are 2, -2. So when it's a position vector, remember that means the initial point is at the origin, and basically this is telling me the terminal point is 2, -2. So that would be right here. And you can see this is the same vector V. I've just translated it. I've just moved that initial point to the origin. And then now it's a little more easy or more straightforward for me to see the direction that it's going in, as well as its magnitude, its length. Okay? Good. So let's just get rid of this. We have no room for it. And we'll move on to example B. So here again, we have points P and Q, initial and terminal points, and they want us to write V as a position vector. So we're going to do that by taking, this is the terminal minus the initial point. And make sure you use the correct notation for a vector. So starting with X, I'm going to have 1/3 minus -2/3. And then for the new Y component, I have -2/3 minus 4/9. So 1/3 minus -2/3, that's 1/3 plus 2/3. And then -2/3 minus 4/9, that's -6/9 minus 4/9. And so the final components are going to be 1/3 plus 2/3, that's 1. And then I have -10/9 for the Y component. Okay, so you don't call them coordinates when you're dealing with a vector, you call them, that's not right at all. You call them components. Okay. Good. Now, a vector having a magnitude of 0 is called a zero vector, and it's denoted by boldface type 0. And a zero vector has no defined directions. If you were going to write out its components, you would say zero vector, and both the components would be 0. Okay. Now, we have to discuss the equality of vectors, because the initial position of a vector in space is unimportant. We looked at that example before where I graphed this vector V, and I had the initial point at -5, -2, and then I drew that same vector again with the initial point at the origin. And those vectors were equivalent. We say that two vectors are equivalent if they have the same magnitude and the same direction. So in the figure below, you can see that these two vectors here, V1 and V2, are the same. They have the same direction. They're pointing in the same direction at the same angle, and they have the same magnitude. They're equal in length. But notice here that vector V4 is not equal to V3. They have the same magnitude, right? They look like they're about the same length. However, they have opposite direction. Notice how the arrow is pointing in the opposite way. So what this means is that V4 is the opposite of V3, or we could write V4 equals -V3, or vice versa, okay? So for two vectors to be equivalent, they have to not only have the same length, which is the same magnitude. So when you hear magnitude, just think length, but they also have to have the same direction. They have to be pointing in the same way, okay? Good. Now, graphically, if you're going to add or subtract vectors, there's two ways to do it. As far as adding vectors, one way to do it is add them tip to tail. Okay, so when you add two vectors, you write it out the same way you would add normal quantities, scalar quantities, u plus v. And the result from adding them together is called the resultant vector. So here, look at, I have vector u, and I want to add to it vector v. Well, you have to add them carefully. You have to take vector u, and then where vector u ends, I start drawing the initial side of vector v. And then the resultant, or the sum of them, I go from the very beginning where I started at u up until where I end with v. And that's the quantity u plus v, which we call the resultant vector. Okay. If you want to subtract vectors, u minus v, one thing you could do is take u and add negative v, right? Wouldn't that be the same thing? U plus negative v. So you could reverse the direction of v. Or another quicker way to do it is if you put the tails of u and v together and then draw a vector from the tip of v to the tip of u, completing the triangle as below. So instead of adding them tip to tail, notice I put both of the initial sides together. And then you draw a new vector connecting their arrows. And that vector is, you have to be careful. Whichever one it starts at, that's the negative one. So meaning, you see how this started on vector v? That's why it's u minus v, not v minus u. Okay? So that's sometimes a shortcut for subtraction that will be useful later on. All right, some definitions about how to add vectors when they're written in component form. You just add them component-wise. So say you have this vector a1, a2, and you're adding it to another vector b1, b2, you just add the x components, the y components. Subtraction's the same way. If you're going to multiply by a scalar, then you can just distribute the scalar inside. You see that? If you're going to take the opposite or reverse the direction of a vector and you're multiplying by a negative, then you just distribute the negative to the components. And this should be bold. This should be bold, or just put the vector sign over it. The zero vector is 0 plus, or 0 and 0 for both its components. All right, and then here's some of the properties for addition and scalar multiples of vectors. So property 1 tells us it's commutative, it's associative. Here is the identity property. All of these should actually be bold because these are vectors. So if you want to add in little arrows or just remind yourself, these are all vectors, okay? This is all bold. All bold except for m and n, which are scalars. Okay, so everything else is a vector. All right, moving on, let's do some examples now. So find a plus b, a minus b, for a plus 5b, for a minus 5b, and this means the magnitude of a when a equals -2, -3, and b has components 1 and 5. Okay, let's go in order. So a plus b is the first thing we need to find. So a plus b is going to be -2, -3, plus 1, 5. So I'm just going to add the components. So -2 plus 1, -3 plus 5. So this is going to be -1 and 2. Okay. Then we need a minus b. So a minus b is going to be -2, -3 minus 1, 5. So that's going to be -2 minus 1, -3 minus 5. So that's -3, -8. And then moving on, now I need to do 4a plus 5b. So that's going to be 4 times a would give me -8, -12, plus 5 times b would be 5, 25. And then hopefully you guys can just add them together in one step now. This would be -3, 13. Okay, and then last thing is 4a minus 5b. So I would take, I already have 4a and 5b, right? So -8, -12, now minus 525. And this gives us -13 and -37. All right, only thing left to do is find the magnitude or the length of A. And before I give you the formula, I'm going to show you how we can come up with it. That way, hopefully you remember it longer and it makes more sense to you. So remember, the magnitude of a vector basically is its length, okay? And vector A, it's a position vector, the way it's written that way. And it has components -2, -3. So vector A, initial point is at 0, 0. -2, -3 is the terminal point. Here's the vector. How could I figure out how long it is? Well, notice here we have a right triangle, yes? And the length of A is the hypotenuse of that right triangle. This side has length. Well, technically it's -3, but the negative doesn't really matter in this case, right? But I'll put it. And this is -2. So if I want the magnitude of A, I'm just going to take the square root of -2 squared plus -3 squared. Okay, so that's going to give us the square root of 4 plus 9, which is rad 13. Okay, so here's the definition now that we already know what it is. The magnitude of a vector A with components A1, A2, denoted by, it looks like double absolute value bars kind of, right? Around A is given by taking the square root of A1 squared plus A2 squared. And the numbers A1 and A2 are called the components of the vector A. Okay, so now let's just practice finding the magnitude for a few more vectors to make sure we understand how to do it well. So find the magnitude of the vector A here. So the magnitude, make sure you write it out properly. Using the correct notation, magnitude of A is going to equal the square root of -2 squared plus 5 squared. So that's going to be the square root of 4 plus 25, which is rad 29. Okay, looks good. Next one, we need the magnitude of A minus 2B. So I need to first figure out what A minus 2B is. So we have magnitude of, what's A? A is 2, -5, minus 2B is going to be -6, -4. I'm going to subtract them first before I take the magnitude. So 2 minus -6, that's 2 plus 6, that's 8. -5 minus -4 is -5 plus 4, so that's -1. So this is going to be the square root of 64 plus 1. So this is rad 65. Okay. So notice the magnitude of a vector is always a scalar, right? It's just a number. It's always a scalar. And it's not negative. So it's a non-negative scalar. Think about it. If it represents the length of something, it's not going to be negative. And it will never be, well, it could be 0 for the 0 vector. This is true, but not negative. Okay. Next, we have another definition. A unit vector is a vector of magnitude 1. So basically, its length is 1. And we have two special vectors. This should be bold, I and J. And when you write it by hand, you put a little hat on it. So and you say I hat and J hat. And they are unit vectors defined as following. So I hat has component 1, 0, and J hat has components 0, 1. Okay, and what this means is now you can rewrite any vector A1, A2 as A1 I hat plus A2 J hat. And if you want to see why, remember, if I start here, A1 I hat plus A2 J hat, I hat is defined to be the vector here, 1, 0. So I can write A1 times the vector 1, 0 plus A2 times the vector, well, what's J hat? 0, 1. 0, 1. And then using my rules of scalar multiplication, this would be A1, 0 plus 0, A2. And then I can add these together. A1 plus 0 just gives me A1. And 0 plus A2 is just A2, which is the vector A to begin with. So that's just another way of writing out your vectors. Okay, just understand it, and then if you don't love it, it's okay. You can switch to component form if you prefer. Okay, so let's work on an example here. Find a plus b, a minus b, 4a plus 5b, 4a minus 5b, and the magnitude of a. So all the same stuff they asked us for before. When a is negative 3i hat plus 2j hat, and b is 3i hat minus 5j hat. So if you don't like this I hat, j hat notation, which most students don't, then you can rewrite it. We'll write a, vector a, with components negative 3, 2, and then vector b has components 3, negative 5. Okay, and then maybe it'll be a little more user-friendly for you, which is fine. So let's start off with a plus b. So a plus b, look how good I am writing all the arrows on top. Make sure you do that. So a plus b is gonna be, we have negative 3 plus 3, and then 2 minus 5, which gives us 0, negative 3. Okay. And let me just show you, if you left it with I hat and j hat, it's really not terrible, okay? So a plus b would be negative 3 I hat plus 2 j hat, that's a, plus b is 3 I hat minus 5 j hat. And you add them together the way you combine like terms with variables. So negative 3 I hat plus 3 I hat, that's 0 I hat. And then I have 2j hat, negative 5j hat. So that's negative 3j hat. And notice that's the same as what we got here. See? So it's just an alternate way of writing out vectors, and you're going to see both used a lot if you continue in math. Okay, a minus b. I'll just switch though and use the component notation. So we have negative 3, 2 minus 3, negative 5. So negative 3 minus 3, that's going to be negative 6. And then 2 minus negative 5, that's 2 plus 5, so 7. All right, looks good. Now we need 4a plus 5b. So for a, can we do that in our head? 4 times this vector, just take the components, multiply by 4. So that would be negative 12, 8 plus 5 times b. So multiply each of those components by 5. It's going to be 15, negative 25. Okay, then we're going to add the components. So negative 12 plus 15, that's 3. And then 8 plus negative 25, that's negative 17. All right, let's see. So we did a plus b, a minus b, 4a plus 5b. Now we need 4a minus 5b. So same two vectors from above. I'm just going to switch this to subtraction now. So negative 12, 8 minus 15, negative 25. So let's see here. So negative 12 minus 15, that's going to be negative 27. And then we have 8 minus negative 25, so that's 8 plus 25, which is 33. All right, looks good. Only thing left, I mean, we got to make these people happy. Only thing left is magnitude of A. Okay. So magnitude of A, remember A has components negative 3, 2. So it's going to be the square root of negative 3 squared plus 2 squared. So it's going to be the square root of 9 plus 4. So rad 13. Okay, good. Now we're going to mix some trig in here, right? So formulas for the horizontal and vertical components of V. So we're going to say theta is the angle drawn in standard position, meaning from the positive x-axis, and we're drawing counterclockwise direction to the vector V with components V sub x, V sub y. Then the horizontal component, Vx, is equal to the magnitude of V times cosine theta, and the vertical component, V sub y, is equal to the magnitude of V times sine theta. I'm going to draw you a quick picture. It's going to make perfect sense. Are you ready? So I'll just draw it in the first quadrant to make life nice and easy. Here's my x-axis. Here's my y-axis. Here's my vector V. Okay? This is V. This vector has length magnitude V. Okay? Now, V is written in component form Vx and Vy. The length of this side and this side can really be thought of as two vectors being added together, right? This is the horizontal component, and this is the vertical component. So this is Vx, this is Vy, here is theta, okay? If you wanted to get cosine of theta, you would take adjacent, which is Vx, over hypotenuse. You wouldn't put vector V, it's a vector. So as a scalar, the length is going to be magnitude of V. So that's why Vx is magnitude of V cosine theta. And then similarly, vertical component, Vy, would be magnitude of V sine theta. Okay, and we've already seen a connection for a while now in our studies that the x values are linked with cosine and y values are linked with sine. So it should make sense that they have this relationship. Okay, so let's look at an example. Given the magnitude of the vector V, which is 425, and the, I think that should be angle, not able. Angle from the positive x-axis is theta equals 36 degrees and 10 minutes. Find the vertical and horizontal components of the vectors. Okay, so horizontal component is going to be magnitude of V cosine theta, which is going to be 425 times cosine of 36 degrees, 10 minutes. You can do that in your calculator. And then for the minutes, remember you can take 10 divided by 60, or if you have that key on your calculator, you can just do it directly. And you should get about 343.10. And then for the vertical component, take magnitude of V sine theta. So you would have 425 sine of the same angle. And if you're slick in your calculator, just push the arrow upwards and switch the cosine to sine so you don't have to retype everything in. And this is about 250.81. Okay. Good. Next example, find the smallest positive angle theta from the positive x-axis to the vector V with components -2 and -2 rad 3. State the vertical and horizontal components. Okay. Well, what quadrant is this vector's terminal side in? Let's think about it. So notice both the x and y components are negative. So this is in quadrant 3, right? And I know tangent of theta is equal to the vertical component divided by the horizontal component. So that would be -2 rad 3 over -2, which is rad 3. So what angle has a tangent of rad 3? Tangent of what angle is rad 3 and is in quadrant 3? So the reference angle would be a pi over 3 reference angle. So theta would have to be 4 pi over 3 or 240 degrees. Okay. And then they wanted us to state what the vertical and horizontal components were. And they're already there, right? So we know the horizontal component was -2 and the vertical component was -2 rad 3. All right, nice job. That's pretty much the meat of the lesson. We're just going to look at 2 more applications and then that's it. So a human cannonball, of course that's what we're doing, a shot from a cannon with an initial velocity of 35 miles per hour at an angle of 30 degrees from the horizontal. Find the magnitude of the horizontal and vertical vector components of the velocity vector. So this is something to keep in mind, especially if you study more math and physics later on. Velocity is a vector, acceleration is a vector. All of these quantities are vector quantities, which is why it's important to understand them. So velocity is a vector, and they're telling us we initially have a velocity of 35 miles per hour. That's the magnitude. Okay. And then they told me this human cannonball is shot at an angle of 30 degrees from the horizontal. So theta is 30 degrees. And they want us to find the magnitudes of the horizontal and vertical vector components. So horizontal component is going to be magnitude of v cosine theta, which is going to be 35 cosine 30 degrees. So we have 35, cosine of 30 is rad 3 over 2, and that doesn't simplify, so that's done. And vertical component is going to be magnitude of v sine theta, so that's going to be 35 sine 30. Sine of 30 is 1/2, so this is 35 over 2. All right. Good. And last example, an arrow is shot into the air so that its horizontal velocity is 52 feet per second. You know what? I was so naughty. We need to put units here. Miles per hour, miles per hour. Good. I wouldn't have slept properly without that. Okay. An arrow is shot into the air so that its horizontal velocity is 52 feet per second. So that's the horizontal component, 52 feet per second. And its vertical velocity is 43 feet per second. So Vy is 43 feet per second. Find the velocity of the arrow. So what they want is magnitude of the velocity. We can write vector V as 52, 43, right? We have the horizontal and vertical components. So how do I get its magnitude? By taking the square root of the sum of the square of its components. It's a mouthful, but basically you just find the hypotenuse, right? So 52 squared plus 43 squared. Punch it in your calculator. You should get square root of 4553, which is approximately 67.48. And don't forget your units, feet per second. Okay. Magnitude should always be longer than each of the components, right? Because it's the hypotenuse, if you want to think about that triangle that we drew earlier. Okay, so that concludes the lesson on vectors. We're going to do a little bit more involving the dot product in the next video, so stay tuned.